Hello everyone! In this video we will continue to examine topic 1.1 measurements in physics, and in particular we will focus in on the concepts of orders of magnitude and estimation. So, this is the first time in these lecture notes, if you're starting with topic 1, that you will have seen these worked examples. A quick word about those. In these worked examples that I embed in the notes, I would strongly encourage you to always pause the video when we get to them in the notes, and to handle them in the following way. These examples are designed for you to sort of practice, and what I would recommend is pulling up those notes locally and going through them one by one, sort of either zooming in or covering up part of the screen, and simply trying out the problem. So, for example, in these examples, we're going to evaluate each of the calculations. Okay, so in the first, you're asked to evaluate this. That just means give an answer to this calculation, all right, and represent it appropriately. So you go ahead and you do so. You read that question. You've covered up the solution for yourself. Okay, however you need to do so on your screen. You try it out. You write it out in your notebook. And then you scroll down to the solution. And you take a look at the solution. And sometimes I will sort of talk you through a solution of an example problem. But more often, I'm just going to rely on these worked examples and encourage you to sort of work your way through them. When we have time in class, we'll certainly go over some of them in more or less detail. But these worked examples are embedded in the notes for a reason. If we don't discuss them, you are still very, very strongly encouraged and required, in fact, to work your way through them as best you can. If you end up with questions on them, so let's say you're not sure why the answer to this is 1.75 times 10 to the 6th, if you're not sure about that, then you can always star it and ask that question in person or in class. And that's what I would encourage and require you to do when we hit a set of worked examples. Okay? We won't always have time to go through them all, either in class or outside of class. But I would encourage you to treat them like they were sort of questions and problems immediately following any section of notes. And I tend to embed them right after you have the ability to do them, so that you can sort of go through them and use them to test your knowledge. I pull them from several different textbooks, some of which you may recognize. I would also just, because this will definitely come up, every once in a while the solution will be wrong. I will try to note it down in the notes if I've seen it or if I know that it's wrong, but it does happen occasionally, so just be a little bit careful. If you've got a question, ask it. All right. So I had promised in this video we would begin to talk about estimation. And estimation is a funny skill. It turns out that estimation is incredibly, incredibly important in physics in a lot of different ways. You will occasionally be required sometimes to estimate answers to arbitrary problems, the nearest order of magnitude. But the only way to get good at this, the only way to get better at this, is to use it. And here's my piece of advice. To develop your skills in estimation will take us several years, okay? You will get better and better at it. But I would encourage you to get in the habit of stopping when you complete a problem and simply asking yourself, does this answer make sense? Is it in the ballpark of what's reasonable? And how do you do that? Well, often you can do that by estimating, by making some simplifying assumptions about the values you're given in order to get a nearest order of magnitude answer. This skill is built fundamentally with time and deliberate practice, and there are a whole bunch of simple example problems in the homework that will allow you to do this. So here's a set of example problems and worked examples with solutions, and we're going to discuss this first one just as a sense of how you might go about solving these kinds of problems. But I will say that the others are problems you should go through yourselves. All right, so let's talk about this first one for a second. This first one says, estimate how many grains of sand are required to fill the volume of the Earth. it gives you a rough radius of the Earth. Okay, radius of the Earth rounded to a single sig fig. Now, here's something important. The first thing is to realize that you're being asked to estimate this. You are not expected to get the right answer, and there is no the right answer. There are better answers and there are worse answers, but I don't know how many grains of sand are required to fill the volume of the Earth, and in fact, we don't want and wouldn't expect a super precise answer. Any precise answer you give would had to have been required by some sort of magical knowledge of the structure of the Earth. But that's not the point of this exercise. The point of this exercise is to say, all right, what's the ballpark, right? Like, what's the nearest order of magnitude, right? Is it 10 or is it 100 or is it 1,000? Okay, so how can we do that? Well, we're going to need to make some assumptions and some calculations. The first is to recognize that we're going to break the problem down into different parts. If we want to know how many grains of sand are required to fill the volume of the Earth, then we need a rough estimate for the volume of the Earth, and we need a rough estimate for the volume of sand. Okay, then we can just divide to get the volume of the Earth, to get the number of grains of sand that will fill the volume of the Earth. So that's our general strategy as we sort of think about this question, unpack a strategy, and then take it bit by bit. So the volume of the Earth, well, the Earth is roughly spherical. It's not exactly spherical, but it's roughly spherical, and we know that the volume of a sphere is 4/3 pi r cubed. Now, we're given an r, so your instinct then is to get the volume of the Earth is just plug this value in. And that's not the worst thing in the world, so you go ahead and plug it in, and you get a value, roughly 8 times 10 to the 20th, and this is already rounded. Okay, this is already rounded. Why are we rounding? Because ultimately we only need the nearest order of magnitude. And notice, not only is it rounded to 8 times 10 to the 20th, which I think most students would be comfortable with, given that this value is already rounded, but notice that this value is rounded down. Okay, so this is an important estimation technique. The radius of the Earth is a little bit higher than 6 times 10 to the 6th meters. So maybe we want to round up on the next one. And maybe we don't even know that, okay? But either way, we're going to find the volume of the Earth to the nearest order of magnitude. Here's something else that, so we take 8 times 10 to the 20th, and we round it to 10 to the 21st meters cubed, because we only need the nearest order of magnitude, and 8 is pretty close to 10. Notice then that the exact value of 4/3 and pi never really mattered. Okay, it only really mattered that this was r cubed. That gave us the majority of our powers of 10 here. Okay, 10 to the 21 meters cubed. All right, so then we say, okay, what's the volume of a grain of sand? And in the solution, it says the diameter of grain of sand varies, of course, but we will take 1 millimeter as a fair estimate. That seems reasonable to me. Let's say you took 0.5 millimeter, or you took 2 millimeters. Or something like that. Well, then you're going to get a slightly different answer at the end, but that's okay. If I'm evaluating an estimation question, I'm going to look for your process. And if I can see that estimate in there, then that seems good to me. You can't be, if you estimate 1 kilometer as the diameter of a grain of sand, I'm going to tell you that that is wrong. Okay, so you need to be in the right ballpark. But it depends on what the question is, what a fair estimate would be. So we take 1 millimeter as a fair estimate, and therefore the volume of a grain of sand, and you can tell they're assuming it's a cube here, is about 1 millimeter cubed. Notice this is 1 times 10 to the negative 3 meters cubed. And it's important to recognize that that is 10 to the negative 3 to the 3rd power. Okay, that's 10 to the negative 9, not 10 to the negative 6. So be a little bit careful with this. So then we take the number of grains of sand required to fill the Earth as the volume of the Earth, 10 to the 21, we estimated that, meters cubed, divided by 1 times 10 to the negative 3 to the 3rd volume of a grain of sand. And that gives us a rough order of magnitude estimate of 10 to the 30th. Now, with this kind of a question, if you ended up with 10 to the 28th or 10 to the 32nd, or somewhere in that range, I think that would be a pretty good estimate. Okay, so this one, we're not even trying to get the correct order or the exact order of magnitude. We've got a little wiggle room on that. But if you tell me it's 10 to the 20th, that's significantly off. That is, in fact, a 10 to the 9th, or a billion, American billion, off. 10 billion, actually. And so we might ask you to estimate answers to questions like these. Again, the best way to get good at this is to do a bunch of them, to do things like estimate the number of beach balls that would fill an Olympic swimming pool, or the number of hairs on somebody's head. This kind of skill is super useful in physics big picture, not just for answering this type of question, which you will see on the exam, but for sort of generally getting a sense if the number that you have calculated with your precise calculation is reasonable at all, okay? What would be a reasonable value for the answer to this question is a question we will ask ourselves over and over and over in this class. So I would encourage you to work your way through these examples here, take them one by one, and then check the solution. I would not consider the solution to be gospel. So the solution that is given to these estimation questions, you may get a slightly different value. But if you get a wildly different value, you should definitely unpack the solution that's shown and try to question your own assumptions. See if you can figure out what went wrong. And be prepared for these on sort of questions and tests on this unit in particular. The biggest picture, though, is that this skill will be useful moving forward.